Okay, so we have started discussing search, and if you remember yesterday's two circle representation of AI areas, in that the inner circle had all the core topics of AI, from which the outer circles areas draw their foundations. So search, machine learning, reasoning, and planning, they are in the inner circles, and natural language processing, computer vision, robotics, expert system, they are on the outer circle. Okay. So now, until midsem, we'll be spending time on the topics in inner circle. We have started with search in the last class, and we'll continue that discussion. Now, why is search important in AI? So you can take examples. So, for example, if you take the problem of planning, where some actions have to be taken in the real world, let's say by a robot, then we have a source configuration. I hope you can see the screen, where the three blocks A, B, and C are on the table. And from this configuration, you have to go to a column configuration where A, B, C are in the column, with C at the top and A at the bottom. Now, if a robot has to perform this task, if an agent, even human being, then we have three options in front of us, okay, to pick A or B or C. Now, you might think that isn't it obvious which one to pick, because A is at the bottom of the column, so you pick A. But this involves reasoning. See that a rule is getting applied. If X is at the bottom of the column, then the block X has to be picked. We are applying this reasoning in our mind. Okay, so out of A, B, C, A is the most appropriate choice. And then I pick B, place B on top of A. Then again I have a choice. Should I pick B or should I pick C? Okay, and notice carefully that this requires introduction of new operator. Okay, if a block is on the table, then we call this a pickup operation. If a block is on top of another block, we call this unstack operation. Okay, it is important to have two different operators, unstack and pick, because we would like to capture the word knowledge that B is on top of another block, and that is closer to the goal state I want to reach. Okay. Now, if B is picked up from top of A, then this operation is useless. Okay. But the agent needs to understand that this operation is useless. This is called rational behavior. Okay. We would like to act in such a way that the final intent is assisted by that action. Okay. So picking up B is useless, but where does that knowledge come from? Okay, you have to think uh, on that point. So everything that we take as obvious in real life, when we try to implement it on a machine, they do not seem to be obvious anymore, and we begin to wonder, what kind of capabilities we have been born with to navigate through our life and the world. So picking up B again is useless. So then we pick up C. So between the operation of unstacking B and picking up C, the operation of C should have higher priority. There should be a scoring function associated with these operators, such that picking up C has higher value. And amongst these options, picking up B gets the nod. Okay, gets done. That is because of the scoring function. So do keep in mind this point of operators. The state, okay, A, B, C, all of them on the table is one state, and the goal state is ABC in the column. Intermediate states, there are intermediate states. A, and then on top of AB is a state. C also could have been on top of B, but keeping C on top of A is not helping with respect to reaching the goal. Okay, so how does the agent know that keeping C on top of A will not be helpful for the final goal? Okay, so lots of knowledge is operating in our mind, and lots of inferencing, reasoning, and the sense of how to reach the goal. Okay, so this is important, and then finally C is picked up. Okay, we carry out a pick operation and place it on top of B. So what I would like to emphasize here is that at every state there are multiple options available, and we have to pick up one of the options to reach the goal. There is a notion of goal which is important. Okay, so this is planning, and this is
So, like, is this scoring done for different actions or like the state? Or just
good question. So the operators are the operators are applied so that the state changes, right? And from one state you can go to multiple states. The operators have a score. Okay, the operators have a score, and states also have a value. We'll come to that little later. Okay, and the goal state has a uh, a particular value which indicates that we have reached the goal state. How do you know that you have reached the goal state? Yeah. So this is planning and search involved in planning. Now, today's AI has changed quite a lot, and you should definitely do this exercise of describing to ChatGPT this particular problem. I have three blocks A, B, C on table, and I have to reach a configuration where A, B, C are in a column, C on top, A at the bottom. Give me a sequence of operators. Okay? And you will see that ChatGPT does a very good job. Now, as you increase the complexity, maybe more number of blocks, okay, or a configuration, initial configuration, which is complex with respect to reaching the goal, see what ChatGPT does. Okay, it does all this. Now, there is an interesting problem. Suppose ChatGPT has solved this problem, and then you will think that, oh, ChatGPT is quite intelligent. The problem is that there may be data leakage. Okay, most probably this example of taking ABC to a column configuration is there in the training data for ChatGPT. So ChatGPT has seen this situation being solved. Through what? Through another professor like me who taught it in the class. And ChatGPT, looks at any data that is openly available. Maybe my lecture is now openly available. ChatGPT has ingested it, and now it has to just retrieve that. No intelligence, just retrieves them. Okay, so this is another point to be kept in mind. AI agents may fool us by retrieving and not really reasoning. There is another dimension to this point. Why should I reason again if the problem has been solved before and I retrieve the solution? What is wrong with that? Nothing wrong, except that our reasoning capabilities will not become strengthened. Okay, if you all the time only retrieve information, our reasoning faculty will remain unused. Okay, that's the point. Retrieval versus reasoning is a fundamental point in intelligence. Okay, do read up papers on cognitive science and books on cognitive science, where reasoning, memory, these questions are very deep questions and important questions. By the way, these questions are not new. Human beings have reflected on these questions at least for 2,000, 3,000 years. Okay, so do perform this experiment on ChatGPT. In computer vision, there is search. Okay, how is that search situation? There are many. One of the situations which is very characteristic is what is called the correspondence problem. Okay? Now we have two eyes, left eye and right eye. And at this point of time, my right retina has the image of this whole class. Okay, the left retina also has an image of the whole class. Now, the brain solves the problem of matching point by point. Why is that needed? If you take a point in the left eye and uh, yeah, and a point in the right eye, okay, and then draw two lines backward, okay, at a particular center in the brain, then the angle between them is an indication of the depth of the object. Okay, so this also is true about the external world. So from my left eye, I uh, I send a ray to a point in the external world. I send another ray from the right eye to a point in the external world. The angle between them is an indication of the depth. So depth computation in the brain is happening because of the two images which are getting created in the left eye and right eye. And matching the 2 points is called the correspondence problem. Now, if there are n points in the left eye and n points in the right eye, then it is an order n square problem, right? N points have to be matched with rest of the each of the points has to be matched with each of the n points on the right hand side, and so on. It's called an correspondence problem. Its complexity is order n square. Now, this also requires search because given any point in the left retina, there are n possibilities in the right retina. No? Correct. So this search problem is solved by the brain internally for many things, one of them being a sense of depth computation. If this is not done, we can meet with accident on the road. Hmm? And if it is not done, then I may not be able to, I may not project my voice correctly for people at the back. And of course, I'm assisted by the mic now. So sense of depth is critical for survival, and it involves search. Okay, so this is computer vision. Um, Robot path planning. So this is a very classical problem in robotics, robot path planning. So the robot is, you can see um, at the left hand upper corner, this R is the position, and D is the destination, the lower rightmost corner. So the robot has to reach from the left uppermost corner to right lowermost corner. This is the navigation. Now you can see that at every cell, the robot has four operations: up, down, left, right. Okay, and it has to choose one of these options. There are these two objects which are obstacles on the road, and the robot has to avoid any cell where there is any part of the obstacle present. Okay, so naturally, the cost of going to those cells should be very high, and the cells which lead to the destination should have very low cost or high opportunity value. So this is also a search situation. The robot continuously has to solve a search problem by choosing one amongst the four possible operations. This is robotic path planning. You are with me? Okay. Then uh, here again, if you let's see if we can do this in the class. If you have access to large language models, which have capability of processing both text and image, multimodal large language model, then we may give this picture of the robot and ask the large language model to give a path for the robot from source cell to destination cell. Okay. So the teaching team see if we can give a demonstration. Okay. Or Shana Vishek can, maybe Gemini or something. Let us see if any multimodal large language model can what does it do if this picture is presented and the question is asked. Let's see if we can give a demo. Lot of things can be demoed through ChatGPT and search large language model. Okay, so this you can see the robotic path, which is in red. Language processing also as such. Language processing also as such. And I'm very tempted to give you one example, which I give in the class, and tell you that there is a very large number of possibilities, amongst which you have to find the right one. This is my favorite example in the NLP class. I'll give it to you also. Buffalo, buffaloes, buffalo, buffaloes, buffalo. Let's see if I've written it correctly. Buffalo, 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 buffalo. Yeah, I think I'm missing an E, but that's okay. So, a lot of my ex-students I meet later, they remember me for this sentence. Okay, and many students of NLP, natural language processing, remember the course because of this sentence. Anybody in the class who knows the meaning of this sentence or can infer the meaning of this sentence? Hmm? So you are trying to retrieve. Okay. Okay. You have seen this example and you're trying to retrieve. Okay. Yeah. Hmm? So this is a tree. Okay. Okay. So to answer this question, we have to first look at the meanings of the words. Overall understanding of sentence starts with the meaning of the words. Okay. So let us make it little more interesting. Remove the capitalizations. Yeah. So buffalo, first of all, can be noun or verb. Hmm. So this starts our understanding of the sentence. Buffalo can be noun or verb. When it is a verb, it means to bully. And when it's a noun, can mean an animal, buffalo, okay, जिसको भैंस बोलते हैं इंडियन में, buffalo, or it can mean the city of Buffalo in USA. Sunny Buffalo. Now, does it help? Is it helping you? Let's see the search space. Okay, so there are 8 words here, and each position you have 3 possible meanings. Okay, 2 nouns and 1 verb. So the search space is 3 to the power 8. You have to search amongst 3 to the power 8 possibilities to get to the correct meaning. Okay, so what is the meaning of the sentence? First, you have to solve a search problem. The search problem is, where is the main verb of the sentence? Okay, which is the main verb of the sentence? But let's not go into NLP detail. So this buffaloes, this let me see if it helps you if I give proper stress and pause. Buffaloes, buffalo, buffaloes. Buffaloes. Is it helping? Not helping? Not helping? Huh? Confusing? So buffaloes is one group. Okay, buffaloes is one group. This is buffaloes from buffalo. Buffaloes, buffalo. Okay. Buffaloes. So, so, so this is another group. Okay, this is buffaloes. Yeah. Somebody was almost correct. You have only 2 sets of buffaloes. There is a third set. So the meaning is that buffaloes from buffalo, whom other buffaloes from buffalo bully, in turn bully a third set of buffaloes from buffalo. Okay, this is the main verb. So you are solving a tremendous search problem, actually. Okay, solving a tremendous search problem. So this kind of grouping is called parsing. It is central to understanding sentences. So we begin with meanings of words, begin grouping, then meanings of larger entities emerge. Finally, the meaning of the whole sentence emerges. And if you ask ask chatgpt about this sentence, it comes back with perfect answer. And the reason is that it is making use of retrieval there. This is a very famous sentence, and a lot of people have taught this sentence. It has gone into the training data. Okay, so you see the search phrase 3 to the power 8. Okay. Other? There are. There are. So this is cows. So cow means intimidate. डराना जिसको बोलते हैं. So those cows which other cows intimidate, in turn intimidate other cows. Okay, because cow has 2 meanings. One is intimidate, the other is animal cow. Okay, so there are sentences of this kind, yes. So now that we have discussed buffalo, this sentence should be much simpler. This is the man would like to play. Man can be noun and verb, like can be preposition and verb, play can be noun and verb, and you have to search amongst possibilities. The next example is from expert systems. So expert systems are assistants which help experts. Okay, so for example, you can have medical expert system, legal expert system, and so on. And in a country like India, these kind of expert systems or AI assistants are critical. Okay, so we work with, for example, radiology experts. So they say that we need AI because we cannot cope with the tremendous load of looking at X-ray plates and giving diagnosis. Okay, so now, by the way, reading and interpreting X-ray plates has been automated to a large extent, to a very, very large extent. And in India, the radiologists are not unhappy about it, though elsewhere, radiologists feel insecure about this situation. Now, the expert systems are, are created out of lots of rules. For example, here there is a rule. If the infection is primary bacteremia and the site of the culture is one of the sterile sites, and the suspected portal of entry is the gastrointestinal tract, then there is suggestive evidence that infection is bacteroid. This is a medical rule, and this rule has been created out of a lot of experience on the field by medical practitioners. So here there are two parts to this nugget of knowledge. There is an if part and there is a then part. So the then part can be a cognition decision or an action decision. Okay, so action decision could be a rule that asks the robot to do something if some conditions are satisfied. So here the infection is primary bacteremia. This is one condition which is matched with the current situation. Okay. Now the point is that this same set of conditions on the if part can lead to multiple actions or multiple decisions. Okay, so and then again we have to carry out a search amongst all possible rules matching the condition, and then pick up one of the rules which leads to an effective decision. Okay, so these are many different examples, very critical examples where search is involved, and I would very strongly recommend that you be aware of where search is involved in your day-to-day operation. Okay. Now, let's get into the algorithmics, data structure, algorithmics, and the formalization of the search algorithm. So when we discuss search, we have to discuss the building blocks of search. So the first important concept with respect to search is the state space. Okay. The graph of states, they express the constraints and parameters of the problem. So I'll illustrate all these basic concepts through an example. Then there are operators which transform the states from one to another. Okay. The start state is special where because the search algorithm begins to operate from there. The goal state is also special because the search terminates there. Now, the goal state is depicted as a set because the goal states can be multiple. Okay, for your problem, you may be happy with multiple goal states. Cost is the effort involved in using an operator, and the optimal path is the least cost path. So we are ultimately interested in the least cost path. Okay, so this is the setting. State space, operator, start state, goal state, cost, and optimal path. This is the step towards formalization. Let's illustrate all this with an example. Yesterday, I mentioned the 8 puzzle problem, and this is the problem that will be your first first assignment example, okay, where you implement A star and show how to go from the start state to the goal state. Now, in this example, we see that this is the configuration 4362185. In between, there is a blank here. We would like to reach a destination configuration 1, 2, 3, 4, 5, 6, 7, 8. Now you can see that in going from start state to goal state, you will have to maneuver all the tiles in the state. Now, for this problem, the state is very natural. The state is simply this matrix where 3 by 3 matrix where the cells are filled with the tile values. Okay, so this is the state. And the starting state is given here. From here, you will have to go to the destination state, which is also very well described. What are the operators? We remarked yesterday that a very nice intelligent step is to look upon the fact that the blank space moves, though in actuality we move the tiles. So if the blank space is moving, then we think of 4 operators. L, blanks moves left, R, right movement, U, up movement, and D, down movement. So our goal is to find out the least number of operators by which you go from the start state to the goal state. Right? This is the least number of operators. Now, for each of these operators, we associate a cost. The cost is 1 for each of these operators. Now, here you have a leeway. Maybe some operator is more costly, so you can encode this in the C function. Okay, so suppose for some reason going upward is more costly, then you can make the cost value more than other costs. Okay, so here the state space is clear. The state space is the collection of all these matrix configurations. How many possible states are there in this search space? How many? 9 factorial. Okay, and the number of operators is 4. We want to find out the least cost path. So this is a clearly defined problem. There is another well-known problem. All these are from the textbook. Okay, the textbooks are mentioned in the website. So this is the missionaries and cannibal problem. There is a river, and on the left side, left bank of the river, there are 3 missionaries and 3 cannibals. Okay. There is a boat which these missionaries and cannibals have to use to go from left bank to the right bank. The constraint is that the boat can carry at most 2 people, and also the number of cannibals should never be more than the number of missionaries on any side of the river, because otherwise the cannibals will attack the missionaries and eat them. Okay, this is the constraint. At most 2 people on the boat, and number of cannibals should not be more than number of missionaries. So this is also a search problem. Why is it a search problem? Yeah.
Both of them in the board, or like any company.
Yeah.
So you have to search among both of
them. Yeah, right. So, but to address this properly, you have to begin with the state first. What is a good state description? So let's go to the state description. We propose the state to be the number of missionaries, number of cannibals, and P, the position of the boat. M is the number of missionaries on the left bank. C is the number of cannibals on the left bank, and P is the position of the boat. So the start state is 33L, right? 33L, and the goal state is 00R. So do you see something intelligent happening there? This is something very basic is operating here. It's called the closed world assumption. Okay, closed world assumption. So we say that 33L to 00R achieves the purpose. What is the assumption here? The missionaries and cannibals are either on the right bank or on the left bank. Okay, nobody has fallen into the river or nobody has disappeared suddenly. Okay, only these possibility exists. This is called the closed world assumption. Also, there is this important notion of relevant and irrelevant attribute. For solving this problem, is the color of the water in the river important? Is it important to know what dresses these cannibals and missionaries are wearing? But all this information will be available. Okay, if I present a picture, then all this information will be available. One of the signs of intelligence is to know which features are relevant, which are not. This is a tremendous ability of intelligence. Okay, so is the speed of the river relevant? So you're thinking, right? So some features, some attributes may or may not be relevant. There are gray areas also. Okay, what are the operations? M2, two missionaries take the boat. M1, one missionary takes the boat. C2, two cannibals take the boat. C1, one cannibal takes the boat. MC, one missionary and one cannibal takes the boat. So all these I've written here, but it would have taken you some time to decide the state and the operators if you had to do it ab initio. Okay, it'll take you some time. And some states are more efficient than other state design. It's a design problem. So the search tree will look like this. 33L is the start state. And from 33L, I can apply operator C2, where two cannibals are taking the boat. When they take the boat, then the boat is on the right side of the river. So R is the position of the boat. Two cannibals have gone. So on the left bank, only one cannibal remains, and three missionaries remain on the left bank. MC, one missionary and one cannibal goes. So 2R, two missionaries, two cannibals, and right bank for the boat, and so on. Can you apply M2 to missionaries? It will violate the constraint of the problem. Okay. Can you apply M1? Violate the problem. Can you apply C1? Why not? Why C1 is not useful? You have to again come back. Okay, somebody has to bring the boat back. Okay. The third problem is that you have black blocks. Okay, B are three blocks, WWW are white blocks, and there is an empty block. The state where we want to reach a state where no B is to the left of any W. Okay, none of the B's is to the left of the W. And there are two operators. A tile jumps over another tile into the blank tile with a cost of 2, and a tile translates into the blank space with a cost of 1. These are the only two operators allowed. Okay. And therefore, now in the first configuration itself, you have a search problem. The rightmost W will slide into the blank, or the last but one W will jump into the blank. You see, there are two options available, and you have to choose one. Okay, so all these three problems you will implement in the lab and run the A* search algorithm, which we are going to do very soon. Now, we have talked about search in language processing, search in computer vision, and so on. The main problem of applying AI to the real life is that most of the time the search space, the state, and the operators are not clear. Okay, so suppose one of you eventually want to become an entrepreneur. You want to have your own startup, or maybe one of you want to become a world famous computer scientist through your research. So you have to reach that state. You are in a state of being a student now. and you want to reach one of these two states. Do you have a clear description of the state in the form of a tuple? Okay, a clean mathematical description of what state you are in and the state that you want to reach. Do you have it? Do you have a clear description of the operators you have to use? I have to get good grades in my courses. That is one of the operators. Does it guarantee that you will become a world famous computer scientist or a world famous entrepreneur? Does it guarantee? You don't know. Okay, you are searching for a path to a goal. Many times we do not know the goal also. I don't know how many of you know what you want to become eventually. Okay, so those are the interesting questions which this formalization of search does not address. But still, it is a useful discussion because it shows how to formalize at least a part of the problem. Okay, so the interesting cases are where the states and the operators are not known or they're probabilistic. Okay, so the probabilistic search algorithms are also very interesting. Okay, let's proceed. So we have just 5 minutes. I think we'll stop here for the next class. So a few announcements. The lab will begin from next week. The lab is on Thursday. Okay, on Thursday. And the lab all the assignments and the final lab project will be conducted in groups of 2. So please form your partner, groups of 2. Okay. What is the class size? Is the class representative here in the class? What is the class size? 200? About 200. So there will be 100 groups. And in the lab, you will do all your assignments and the projects in groups of 2. So please form your groups, and an Excel sheet should be circulated, okay, to get the group names. Okay.